Hello everyone, and welcome to the Foundational Statistics for Forensic Toxicology webinar series. Throughout this series, we will hear from Sue Paring, Quality Manager with the San Francisco Office of the Chief Medical Examiner, and Aria McCall, Technical Lead with the Tarrant County Medical Examiner's Office. Today is Session 2, Distributions and Standard Deviation. Without further delay, I will turn things over to our presenters.
Well, good morning, good afternoon, good evening, wherever you might be joining us from. Today we're going to talk about distributions and standard deviation, like you just heard, so welcome back. I'd like to start today with a quote. Real knowledge is to know the extent of one's ignorance. And you may be familiar with the 4 stages of competence. I want you to consider the 4 stages of competence that you see here. When learning new skills, we start in the upper left-hand corner here, unconscious incompetence, where you're unaware of the skill and your lack of proficiency. In other words, for lack of better words, ignorance. And as we grow in our understanding, we move into what's called conscious incompetence. You're aware of the skill, but you're not yet proficient. Then we move into conscious competence. You're able to use the skill, but only with effort. And lastly, into unconscious competence. Performing the skill becomes automatic. You'll notice there's no arrow here because we don't want to end up back in unconscious competence. But this cycle and this pattern repeats itself as we learn new things. So it's our hope that with this series, you continue to move in the direction of the arrows. Wherever you are on this topic, you move from one realm to the next. And from our time together in session 1, this is us. This is who's represented among the attendees that came to session 1. You might have joined us live for that and participated in this poll. You might not have. But again, let's start with kind of that unconscious incompetence, which is shown here in this dark blue. And sometimes that's like blissful ignorance, right? We're glad it's not our responsibility. We're hoping to move you into the category of I'm curious, but it seems like a lot. And as you learn, maybe you do it but aren't sure that you're doing it the best way. And we hope to eventually move everyone into this I crush it, give me all the numbers category. And maybe then you'll develop the next series and the series on statistics for forensic toxicologists. So what do you see when you look at this piece of artwork? It's titled All is Vanity from 1892. Do you see a skull because you're a toxicologist? Or do you see a woman at a vanity looking at her reflection? Or do you see both because I asked the question and now I've drawn your attention to both of them? This type of artwork is called ambiguous figures, also known as reversible figures or bistable figures. When you see the word sample, though, what do you think? How about these other ones on the screen? Right? In toxicology, we know these terms. They're familiar to us, and this ambiguous phenomena is present with us as well when we, as toxicologists, see these terms in journal articles, statistics textbooks, etc. And so when we see the word sample as a toxicologist, well, we might think a specimen, a biological specimen. In statistics, we're talking about a subset of population. This is one of the terms that Aria covered in the previous session. When we see the term test, we might be thinking an assay or a method as a toxicologist, but in statistics, you might be thinking of what a hypothesis test might be. Similarly, for error, we're talking about mistakes or uncertainty. These are the associations, not really a definition, but the associations we have in toxicology for this term. Where in statistics, there might be an actual calculation behind it in a concept of standard error. And lastly, goodness of fit. In the toxicology realm, we might be thinking about calibration curves, least squares, regression. You might be thinking fitness of purpose of a method for a particular application. But in statistics, we have kind of this concept of whether or not a particular probability distribution fits the observed data very well. And so we're kind of doomed to have this ambiguous relationship with some of these terms. I say doomed, I mean, it's not so negative, really. We have to balance and understand that when we come from the perspective of toxicology, we often have this first association with these terms, and there's many more like this. This is just a couple of examples to kind of bring your attention to the fact that if it's confusing when you see these terms being applied in the realm of statistics, It's not really a problem. We just have to become aware that both of these we have to hold in our minds and apply them correctly as we move forward. So let's start by understanding some types of data that we produce or that is encountered in forensic toxicology. Much of the work that we do is in the realm of quantitative analysis. This is obtained typically through the use of calibration curves or some sort of calibrated equipment. We produce quantitative analysis and review it when we're looking at quality control data. We might use replicate measurements, and certainly in validation studies, we produce potentially lots of quantitative data that needs to be analyzed and some conclusions drawn from it. We also have another source or another type of data that we produce, which I'm calling here aggregate data. This might be long-term QC data, and it might be something like proficiency tests where interlaboratory comparisons are performed. My lab, your lab, 300 other labs that might be participating in a proficiency test. And this data is aggregated together. What does that do for us? How do we describe this collective data? Or it might be something like stability studies. Again, long-term, over a long period of time. It might be, the stability of a particular drug in a solvent or in a biological matrix, right? This kind of aggregate data is another type or another source of data that we often deal with. And last but certainly not least, I think it's important to consider business metrics as well. Statistics can be a powerful tool for us to understand and to help others understand changes to our caseload, to our workload, to staffing with the opioid epidemic and with changes in each of our geographical areas. Business metrics is a powerful tool, and data there can be very valuable. Other kinds of business metrics that might be relevant, turnaround times, and in the consideration of investing on new equipment, new software, on additional warm bodies in your laboratory. Cost benefit analysis and return on investment are also considerations. So when we talk about statistics in forensic toxicology, we may be talking about quantitative analysis, aggregate data, or business metrics. And how we design systems to house, track, record, visualize, and analyze this data can significantly affect what we can glean or what conclusions we can draw from them. And visualization is certainly a powerful way to bring data to life. The three examples you see on your screen are here from JAT, the Journal of Analytical Toxicology. And this might be the types of data that you're used to handling. The text is really small, don't worry too much about it. We'll come back to this. But I also wanted to highlight that the TAFT, the International Association of Forensic Toxicologists, the regular publication from there, the TAFT Bulletin, has an 8-part series that Brigitte will be touching on in session 3. But I also wanted to highlight that starting in 2019, there's kind of an 8-part series on a statistics primer for the forensic toxicologist, a phenomenal resource, and also a printed resource that you can refer to again and again. There are other favorites of mine that you'll hear me talk about throughout this session and others, and we'll be putting and collecting those resources to make available to you all as well. But before we get into kind of the toxicology specific applications, let's review a little bit of where we had started. In session 1, we reviewed some of these terms, and today we'll dig more into standard deviation and its related concepts. So where do we start? We can start with the concept of dispersion. Now, when I say dispersion, or we talk about different measures of dispersion, we're talking about something that conveys information about the amount of variability present in your data. This could be quantitative, it could be qualitative, but typically we're going to be talking about quantitative data as we describe these measures of dispersion today. But you can think of it very generally. If all the values are the same, we don't have much dispersion, or we have no dispersion. They're all identical. And if they're not the same, then there is dispersion. Now, the question is how much? Another way to think of measures of dispersion is to think about its variation, spread, or scatter. And if you're more of a visual person, you might just think shape. How do you describe dispersion? You think of the shape of data that you're talking about. Well, if we're thinking about the shape of data, we've got to consider the axes that we're talking about. And typically, as we talk about distributions, our focus is on frequency and the value or the units of whatever it is that we're measuring. So on our y-axis here, we have frequency, and along the x-axis, we have value. And this can be called a density or frequency plot. And a graphic like this might be a familiar territory for you. We have three sets of data here with the same axes, same quantitative scale, all plotted together. And to describe their dispersion differences, let me ask you this, not through a poll question, but just to consider, how are these similar? How are these different? How are they similar? Well, they have the same mean, and you'll see the one label here, and they're all centered around here. They're symmetrical. You might observe that too. The left and right sides are similar, and all three of them share the same mean. They also share the same mode, right? The most frequent value here, where the highest frequency is found on the green chart, the blue chart, and the red chart, actually all have the same value. Their individual frequencies are different, right? With red being the most frequent at that mode. However, respective to that distribution or that particular set of data, they have the same mode. They all are centered around the same mean and they have the same mode. So if we focus on the far sides of the dotted lines here, area out here and the area out here, I'm going to focus on this side here just because it's not crowded with other text. We can ask the question of how much of the data is found here in the extremes. It's symmetrical, so over here is the same, right? So while the median, the mean, and the mode are all the same here, the differences in dispersion are quite pronounced. It may be hard to see with them overlaid, but if you focus on one at a time, you can see how much data, right? How many data points, how much is under this curve for the green chart is quite different than blue, is quite different from red, right? So let's start with what we know best. Some say, hey, better the devil you know than the devil you don't know. So we'll start with normal distributions, just to discuss some terms about dispersion first. And then we'll get into what makes a distribution normal and what to do with other types of data. Maybe some of these traces here or other non-symmetrical distributions. So the tools that we have, or at least some of the tools we have to describe dispersion, include range, standard deviation, coefficient of variation, and z-scores. The simplest being range. It's just the difference between the highest and the lowest value in a set of data. If you're a formula person, you can say it's the maximum value minus the minimum value. And it's often described as being inferior to other measures of dispersion. And why is that? Well, whether you have that green trace or this purple trace, the ranges are the same, right? The maximum value is out here, the minimum value is here. It tells you nothing about the shape that's happening in between these 2 points. So whether it's green or purple, the range is identical. Or maybe something like this. Again, the shape quite different, but the range is, again, identical. So it gives us information, but not a ton of information. Now, take, for example, this graphic from Khan Academy, one of my go-to resources on really any concept, but often statistics and some. It's just a wonderful resource and totally free. If each of these data sets from this course here, from the statistics course from Khan Academy, had identical x-axes, I've just plotted them out here. The range of each of these would actually be the same, right? We have frequency on the y-axis, the values on the x-axis, and the scale and the values are the same. The ranges are actually pretty much the same, right? It goes from here to there, but it doesn't tell us anything about the shape. It doesn't mean it's useless, right? But again, it's limited value. So then we have variance. Variance is defined as the relative scatter of individual data points around their mean. You subtract a mean from each data point value, square the difference, add the square differences, divide by the sample size minus 1. Okay, what are we talking about here? Notice there's two symbols up here to describe variance. There's an S and a lowercase sigma, and they're both squared. Now, why the or and why two symbols? Rewind to what we covered in session 1, Aria had addressed the definition of population as the entire group of items, right? And it's represented by a capital N. That's to contrast this with the sample, which is a subset of that population. indicated or represented by lowercase n. So why is that relevant here? We talked about two different symbols for variance, and one of those goes with one of these, and the other goes with the other. So what do I mean? Which one goes with which? Variance with a lowercase s and s squared really is for samples. You notice the lowercase n down here. And if we turn this like word formula into a mathematical formula, this is what we're talking about. So we first have to calculate the mean, right? And then take the difference between each data point and the mean. We square that difference, and then we do that again and again for each of these data points. We add those all up and divide it by the sample size minus 1. You'll notice the lowercase n for sample, right? And the lowercase s and not the sigma for variance. So when we're talking about samples with that lowercase n, we use x bar to describe the mean and s squared, the lowercase s, for variance. Now, how about for populations? Same equation, right? Same concept, the difference between the data point and the mean squared, added all together. But you'll notice here in the denominator, we have a capital N, and it's no longer n minus 1. And this now is the variance for a population. Instead of x bar, we have mu to describe the mean. And instead of an s, we have the lowercase sigma. So if we had a population, let's say, of 9 data points, like shown in this graphic here, what does this look like? To be a little more explicit with some actual numbers, the mean here would be 7, right? And you have data points below it at 3, 4, and so on. And then you have ones above it at 10 and 11 and everything in between. So to perform that calculation to determine the variance, we'd be taking the difference between 3 and 7. So you get -4, and we square it. Now, what happens when you square a negative number? It becomes positive, right? So this is another way to understand this, is that whether you're below the mean or above the mean, and we square it, it's no longer being considered if it's below or above, right? If it's just the relative difference, 3 minus 7, it would tell us that it's negative, so it's below the mean. But when we square them, that all goes away. So it's describing the variance of this data set around this mean. And so the difference here, the calculation here produces a number of 11.1. And so for samples, right, lowercase n, we have x bar and s squared. For population, we use a capital N. The formula is slightly different. And then we use mu to describe the mean and this lowercase sigma squared to describe the variance. So would you really need to calculate the variance by hand? Like, are you scribbling that formula down, trying to figure it out? I mean, we all know that is a calculation that can be done easily by Excel. There are many other tools to calculate standard deviation. So why go into all of this anyway? So while the exact calculation and memorizing that is not something I care to belabor at all, it is critical to actually understand what it is that statistic is measuring. Part of why that's so important is because without understanding what it actually is measuring, we might misuse it. We might misapply it, right? So keep that in mind as we move to standard deviation and continue this conversation. Let's say that this data represented the number of letters in the last name of all of our attendees today. You know, if we did a poll and we said, how many letters are in your last name? You might get a massive set of data that might, center around a number of 7 letters in your last name or something. Well, let's say instead of the 200 or so people online today, we only had 9 participants, and that was the entire population. That's all of us. So we could do this calculation, right? And so the numerator, right, is representing the differences in the number of letters. Maybe your last name is Lee, L-E-E. So 3 letters, and the average is 7. You take the difference, you square it, right? So what happens to the units in this numerator? The units, really, right, letters minus letters squared, is now letters squared. Okay, stick with me. And the denominator, right, was simply the count of students. There's 9 people here today. And so 9 is our denominator, and it has no units. So when you calculate variance, what do you end up? You got letters squared, divided by no units. So the units here is letters squared. And what does that mean? Right, absolutely nothing. The units of variance leave us with arbitrary units that don't really mean anything. So enter the familiar, the crowd favorite, the standard deviation. This is obtained by taking the square root of variance. Now letter squared becomes letters. It simplifies the units of variance and makes it a usable parameter for us that is relatable, that is understandable, that actually means something. And this is often the most common way to express dispersion. So similarly, you notice there's two abbreviations, same concept here. Whether you take the square root of s squared to get s, or you take the square root of sigma squared to get sigma, the same formulas for variance are right there. You just take the square root of them. So there's two more measures of dispersions for us to define before we move on. Now that we have standard deviation, we can calculate the coefficient of variation, or CV. And this expresses standard deviation as a percentage of the mean. It's also known as the relative standard deviation, or percent RSD, but it allows the units of measure to cancel out. Remember that the standard deviation, not the variance, right? We've taken the square root, so no longer an arbitrary unit, but the unit of interest divided by the mean, which is also in the unit of interest, and they cancel each other out when we multiply by 100 to represent it as a percentage. It kind of normalizes it for the data that you're talking about and allows for comparison of dispersion in two or more sets of data. So to bring this back to the toxicology world a little bit, okay, bear with the numbers on this. I just wanted easy numbers for us to talk about. Let's say we're talking about a comparison of two or more sets of data. Let's say two sets of toxicology data in DUID samples. Let's say we're looking at the concentration of fentanyl in drivers and the concentration of meprobamate in drivers. And let's say all of the results are represented in nanograms per milliliter for both. Now, you may already know as a toxicologist that the concentrations expected in these populations or in these samples are quite different by scale. Still nanograms per mil, the same unit, but very, very different scale. Let's say for the sample data set, the standard deviation for fentanyl is 3, and actually, hold on, let me show it this way. Let's say that the range of data might be plus or minus 3 from the actual mean for fentanyl, right? But we know for meprobamate or some higher therapeutic concentration drug that it might be more like plus or minus 30, where the scale of these is quite different. Now, let's assume that the shape and the distribution in this sample or in this group of data that we're talking about, whether it's fentanyl or meprobamate, let's say that the dispersion is actually the same. I really just took this graphic and stretched it out to make that point. But the scale is so different. So what do we do with that? The standard deviation, and this is not representative here, but let's say the standard deviation is 2, and the standard deviation here is 20. But when you look at those numbers, it just seems like, well, that's a lot more varied. When in reality, we can actually calculate the CV to normalize it to relative to its mean, right? 0% for the mean would be the mean itself right here. And it allows us to visualize this on the same scale relative to itself, right? So even if we're talking about two very different sets of data, we can compare the CVs. And so the CV for this on the left might be 20%, and the CV on the right is also 20%. And it's just changing the scale in which we're showing this so we can compare the variance from one data set to the other, even if they're very different. So we've talked about, and sorry for the scribbles here, I like to do handwriting when I teach, but it's hard to do live, so I did it earlier. We have standard deviation squared, also known as, yes, variance, and then standard deviation, right? And a CV that we can calculate. So whether it's variance, standard deviation, or CV, what we're describing is a dispersion of the data set, right? It gives us information about the overall group of data and what the shape or the spread is. But what if you want to know something a bit more specific about one particular data point? How far is this from the mean? It's actually an easy calculation. After all, you've already done it as a part of the variance and therefore also the standard deviation calculation. But what about how far it is from the mean relative to the other data points? You have 100 data points. How do you characterize just that singular data point? This is the beauty of z-scores, or standard deviation index. Sometimes referred to as standard scores, it's simply the number of standard deviations that a given value, x, is above or below the mean. And what do we mean by like standard scores? If we're talking about, let's say, the IQs of two people, one person has an IQ of 102 and another has an IQ of 165. That in and of itself doesn't tell us a whole lot unless we can kind of compare it to the population, right? Is 102 high? Is it low? Is it relatively high? What percentile might it be, right? These kinds of questions relate a single data point to the population or the sample that it came from. And it allows for comparison of results that ignore the scale of being used. So what is the z-score? You take that value, subtract it from the mean, right? That was the beginning of the variance calculation. How far is it from the mean? And you divide it by the number of standard deviations. And so what does that do for us? Some of this might be very familiar of a 68, 95, and 99 rule. Well, in a normal distribution, this rule applies and is heavily relied upon as a standardized way to understand this dispersion. And the z-score is associated with these concepts of how many standard deviations you are away from the mean. So 68% of the data, right, falls within one standard deviation of the mean, 95% within two, and 99.7 approximately of data falls within plus or minus 3 standard deviations. And in other words, the values of your z-scores when they fall between -1 and 1, right, are going to make up 68% of your data, plus or minus 2 standard deviations, or a z-score between -2 and +2, 95, and so on. So in the example of IQ, if you found that the IQ of 102 had a z-score of -3, you have a concept of, well, relative to the others, we're way down here in the realm of things, right? As opposed to just the difference between that and the mean, you wouldn't necessarily know anything about the shape or the distribution of data relative to one another and relative to that sample. And if you're looking at this and you're thinking, this is where maybe this is related to 95% confidence interval with a K of 2, and you're already thinking about measurement uncertainty, you're absolutely right that this is related to that concept, but you are ahead of the game, and we'll dig into that a bit more later on in session 4. If you're not thinking about it, great. You don't need to think about it right now. So I keep reiterating for a normal distribution. These expectations around dispersion don't really apply when the shape of the data isn't normal. You can't see my air quotes, but I do want to emphasize that. So what happens when it's not normal? Let's say the blue curve here is normally distributed, right? And if we refocus on the extremes here, you can see that's a fairly small amount. The amount of data, the area under the curve, and the extremes beyond these dotted lines, right, is quite different for each of those, like we talked about earlier. So answer this question to yourself, while the means are the same, the standard deviations are different. Which of these traces, red, blue, or green, has the largest standard deviation? Which has the smallest standard deviation? Right? The largest standard deviation is actually going to be this green trace here, and the smallest going to be the red trace with a blue one in between. And again, let's focus on the blue. And only about 5% of that data exists out there, right? Again, assuming a normal distribution, that at 2 standard deviations, there's about 5% or 2.5% on each side, right? But how about with the green curve? This broad distribution, the standard deviation is greater, right? That was the greatest of the 3 traces of standard deviation. And maybe where this mark is, maybe 20% of your data exists out here, maybe 10% on this side, 10% on this side. And this might reflect a standard deviation of only about 1. So while it's drawn at the same place, right, that might actually reflect only 1 standard deviation for the green trace. If we focus on the red, what's out here for the red trace? looks like 0, right? Maybe that's 4 standard deviations away and there's just no data out there. So while we have many measures of dispersion, they're not all equally usable, right? That 68, 95, 99 rule only applies for normal distributions. So you may recall from earlier that the most inferior but most commonly applicable, widely applicable measure of dispersion is range, right? Whether the red, blue, or green trace, the range can be measured easily for all of them. Now, standard deviation can also be calculated regardless of the distribution. Um, and with individual and independent data points, the mean can be calculated and then used to calculate that standard deviation, right? Now, we often confuse standard deviation with normal distribution. We often kind of associate standard deviation simply with normal distributions because of that 68, 95, 99 rule we just talked about. And it's not that standard deviations are only applicable for normal distributions. It's that the 68, 95, 99 rule only applies to normal distributions, right? And remember, with standard deviations, then we can also calculate or represent it as a CV relative to the mean, and also then we can describe the individual data points as a z-score relative to the standard deviation. So we're talking about normal distributions. I keep alluding to that there are other, right? The traces that we saw earlier were all symmetric, but there are also other types of distributions. What else are there? Well, there's paranormal distributions, or naturally, but really what we're talking about are other realistic distributions here. The lengths of houseflies is shown here, with the frequency on the y-axis and the length in centimeters. It's symmetric. It's not quite normal, but it is symmetric, similar to normal distributions. And the mean, median, and mode are likely all centered in the middle. The dates on pennies, right, and how many show what years on those pennies show what's called a left-skewed distribution. The tail trails to the left. The more recent penny, the more there are. The older, the fewer, right? So produces a left-skewed. And high temperatures in Celsius show somewhat of a bimodal or a two-peak distribution, suggesting that we might have some winter weather, some summer weather, and they're all being plotted together. So you kind of have these two clusters of data, but all plotted as one. The number of state representatives is right-skewed, right? There's more states with fewer state representatives and then fewer states with lots and lots of representatives. Cups of coffee our attendees have had so far today. What kind of shape is this? Is it symmetric, left, or right? If you're thinking left skewed, that's right, right? The trail is off to the left here. I hope you haven't had 3 cups of coffee, but maybe you have. And with these kinds of examples, it's not hard to imagine that data within toxicology is not all normally distributed, right? This last example was individual dye rules. This is somewhat even, you might call it uniform or rectangular distribution, right? So how do I know if the data that I'm working with is normally distributed, right? We have the benefit of the 68, 95, 99. We have other things we can do with normally distributed data. But how do I know if it is normally distributed? And sometimes it's easier to actually assess how do I know if the data is not normally distributed. Well, how do we evaluate that with those 6 examples earlier? One way is to simply plot them. Right? If you have the data or you have the time to go collect the data, you can actually verify whether or not something is normally distributed by plotting. It certainly can give you an idea if you're dealing with non-normal. There are other things you need to do to see if it is normal, but it certainly give you an idea pretty quickly just by plotting them. But let's say you don't have that luxury. Can we apply the knowledge that we have, the theoretical knowledge, our understanding of these concepts that we have to them and project what it might look like? So what do we as toxicologists know about the relative frequency distribution of the 3rd digit of breath alcohol pooled field data? That's this graphic on the left. Relative frequency distribution of the 3rd digit of breath alcohol measurements. What might you expect this distribution to be, right? We're not just talking about breath alcohol concentrations, we're talking about the 3rd digit of such a value. What might you think it is? Feel free to drop it in the chat. Feel free to just answer to yourself. What might that look like? What we find is that it's somewhat of a normal, misusing that word already, somewhat of a similar distribution, right? A similar frequency. We're talking about the 3rd digit. This is a third digit. It's not about the measurement. It's just about you collect all this data. What does the last digit look like? And maybe it's a surprise, maybe it's not a surprise to you that it's pretty flat. They're quite similar. Now, if you take a very different kind of toxicology example, what's the frequency distribution? What shape is the distribution of concentrations of atizolam in DUID cases? What might you think that is? What do you know about atizolam? What do you know about DUID drivers? What do we know about concentrations in this type of work? If you've been around toxicology a long time and you've been studying atizolam, you might have an idea of what this looks like. But if you haven't, and you haven't tested for it or you haven't looked at collective data, um, what shape might that be? Well, it actually looks like this from a 2022 publication, and that's what it looked like. So the theoretical knowledge can get us so far. Sometimes it's very predictable, and it's helpful for us to think through what does that look like? What could it look like? And other times we might not have a good idea based on our theoretical knowledge because the theoretical knowledge just doesn't tell us a whole lot about the actual distribution, right? So what do we do with that? A generalization that we hold often is that when sample sizes are large, right, when they're way beyond 30, when they're big enough, that we have a normal distribution, right? However, I want to really emphasize that this is not a guarantee by any stretch. You saw this graph earlier of the DYD concentrations of atizolam. And the sample size, you can see the number of cases is scale 35. Even just in this one bar in this histogram, we have 33. You have a sample size of much larger than 30. There's all this data here, but it's definitely not normal, right? So if it's not sample size and we don't actually have data to plot, we have to work with what we know. So let's say you didn't collect this, right? Theoretically, we don't know anything about this. And what information might you have? How might you conceptualize the theoretical knowledge that you do have, or place certain assumptions, state the assumptions, and then move forward with whatever you need to once you've identified the distribution. If you have the maximum value, even if it's theoretical, right? Your theoretical maximum, what's reasonable, what you've seen in the literature, your maximum value and your minimum value, but you have no real information on what the outcomes might be in between those, you might start with this very simple shape or this very simple distribution of a rectangular distribution. Whereas if you have a max and a min, but you have kind of a concept of a lower mode and an upper mode. In other words, the most frequent value on your low end might be this value here, and you might have kind of an understanding of what might be most common on the upper mode and everything in between. You end up with a trapezoid shape and a trapezoidal distribution. What if you have a max and a min, but you also have a concept of a singular most likely outcome? Again, this is all theoretical, right? It's projected based on our actual knowledge, theoretical knowledge about whatever topic and whatever data set we're talking about. Here you'd have a triangular distribution, right? You've got your max and your min here, your max here, and your most likely outcome, which forms a nice triangle. And this shape, right, is a little more informative than just saying, I have no idea, I don't have the data, I don't know anything about it. It even layers upon what you might know about the range to give an idea of the shape or the distribution of data that you're working with. So whether you're dealing with a normal distribution where you have plenty of data and it's been shown to be symmetrical and normally distributed, that's this tall trace here, or maybe a T distribution where your N is not so high, or that the shape of it is not so normally distributed, typically when the N is lower, or you might have rectangular, trapezoid, triangular distributions. And if we layer these on top of each other, you can kind of see how it starts to mimic the shapes here. In other words, when you have potentially symmetric data, even if you don't have all of the information, you can at least start to project based on what you do know, what this might look like. So bringing us back to session 1, we have the years in toxicology that you all provided and plotted here the frequency on the left and the number of years down here on the x-axis. We had about 50 participants that had, ranging from 0 to 3 years in toxicology, which is our biggest group. Awesome. Well done for attending. Thank you for joining us. And then all the way up out here, which kudos to whoever this is, 48 to 51 years. That is impressive. I hope to be there someday. And we have this beautiful spread of data. And just recapping real quick, what are we talking about here? Is this a right skewed, right tailed, left? Is it symmetrical? Is it uniform? Is it trapezoidal? What shape is this? If you're being sneaky, you might think it's triangular. Here you go. They have a nice right triangle. That's not the triangular distribution we're talking about. What shape is this? Indeed, it's a right skewed, right? A right tail here, a right skewed distribution. So what do you do with that? Um, I might have thought that it would be more normally distributed. I don't know. That was just my guess if I had to guess back when we had issued the poll. So what do you do with this? Well, we can determine the range. Sure. We can look at the high, and the low, and it's, maybe 51 to 0. So your range is 51 or 50. That can certainly be calculated. You can calculate the mean, right? That poll data was given to me as a list. You can calculate the mean of that and figure out what that is. You can calculate the median also, right? How many are on either side of that middle value, but it doesn't actually. This is kind of limited value. Now, standard deviation, right? A great measure of dispersion, definitely an upgrade from range, and kind of our first term. Standard deviation can be calculated, but the information that it gives actually tells us nothing about the shape or the symmetry of the distribution that we're talking about, right? Remember that this is what we're talking about. The standard deviation may be calculated, but for one, certainly the 68, 95, 99 is not applicable. It's not normally distributed. It's not even symmetrical. So while you can make a calculation to determine the standard deviation, what does that really tell us? Right? Something that might be more helpful would be the first and third quartiles relative to the median, right? What's that middle value? What's 25% of the population that's like below that, above that? And it can be a little bit more descriptive to the distribution of values. We're not going to get into that today, but there is another approach. Taking this data and transforming it to see what it could look like. Now, in our house with my 8-year-old boys, transform means transformer cars that turn into robots. And while we're not going to turn this into a robot, we mean that we can apply a mathematical function and leverage it to transform this data, to transform this distribution into a more normal, into a symmetric and a more usable distribution. And for right skewed or left skewed data, this could be done by taking a logarithm or taking the square root. And, I still remember the first time I learned about this concept, and I was pretty incredulous. Like, how does that work? And what does the square root of the years in toxicology even mean, right? Kind of like we were talking about with variance. When you take those units, you take the differences of the number of letters, right? You square it. That doesn't mean anything. However, what it does mean, like we did for variance, is that you can then undo that calculation, right? You take the square root and it becomes usable in the units that we're talking about again. And similarly, for this type of data and for this type of transformation, the same could be said. If you take the years of data from 0 to 51 in this shape, and we transform it by taking the square root of it, what you actually get is something that looks like this. A bit more normal, certainly more symmetric than what we had before. And from there, we could calculate the standard deviation. And then from there, calculate the CV, talk about it using z-scores. We're trying to see where you fit in all of this. And remember that because this data had been transformed, that you would then undo that, right? Undoing a square root, squaring it to then make it usable. If we actually calculated this out to be, whatever the standard deviation was, let's say the standard deviation was, I don't know, 2. If you undo that calculation in years of toxicology, then 2 squared, you get 4, right? So then you can make these calculations a bit more usable, even if you started with data that looked not normal, not symmetric, and it feels like all your tools about dispersion no longer apply. So at this time, I'd like to thank you for your attention. And when you think about these concepts, just be reminded that This dual association and this ambiguous artwork is a good reminder that we're holding two worlds of information in our heads. Many of the times the terms are shared, and that can be very confusing. So take your time with it, find the resources that you like, refer to them often, and stay curious.
All right, thank you, Sue, for giving us a presentation today. If you have any questions, go ahead and put those in the Q&A, and we'll start with a few that we've just recently received. So we had a question about what exactly did you take the square root of in the transformation of the years for the toxicology data?
Yeah, great question. I didn't want to do it all on screen to drag everyone through all of my mousing. But if you imagine that list of data from 0 to 51 years, right? How many of our participants? Every row of data is a person's number of years. And you take each of those values, let's say, I've been in the field for 13 years. You would take the square root of 13, and that becomes my new data point. So you do that for every data point there. And if you plot that the same way we plotted all the other frequency distributions, you plot that, and that's how we got that second graph. Thanks for your question, Heather.
And I think this one is along the lines of the transformation as well. So how do you tell which transformation to use?
Yeah, I won't get into all of that today. I did do a quick search when I was looking at, the years of data. I genuinely thought it was going to be normally distributed. I was like, this is going to be great. We're talking about standard deviation, use the 6895. And I was like, oh, maybe this will be a different example. It's an example of what to do when you don't have normally distributed data. And I would definitely direct you to other resources for that. I'm not going to spit off which ones are which, but I did find that for skewed data, right skewed, left skewed, it doesn't matter, logarithms or square roots, depending on how skewed it is, are effective transformations. And sometimes, what you'll find when you look up these resources is something that's like way more complex than you know how to deal with. Or you might find 5 different approaches to this kind of question. And I would really encourage you, just start with the ones that you do understand, see if it gets you close to that, and then dig into it a little bit more. Keep asking the questions, and you'll find hopefully something a little more useful for you.
Then we just had a comment, and this one may be addressed in some of the later presentations, but I'll go ahead and ask this one. It was a comment about even though the toxicology year's data is not normally distributed, as long as the n is greater than 30, you could apply a central limit theorem to calculate z statistic or t statistic to test hypothesis about the population.
Yeah, I'm not going to get into that today, Jason, but thanks for your comment. There are so many concepts behind these things. And we really want to highlight just the foundational concepts of it to understand what the differences are, what to do when you have some of them, and to also, move people from one quadrant of the stages of competence into the next. It is certainly a journey, and I wouldn't call myself a stats expert by any stretch either. I've learned a lot about it over time, and I've done a lot of on-the-job training. I've really dug into it. I'm a bit of a nerd and really like math, so that comes pretty naturally for me. But it is a continuous journey. So wherever you are in that, just moving along to that next step, finding the resources that you need to move forward on that is the best I can offer.
I think just on that one about talking about how normal it is, or suggestion about running a normal distribution plot for graphically displaying how normal a data set it is. Okay, and then there's another comment about making sure they understood if you have a non-normal distribution, you can transform into something more normal by applying a mathematical operation. Then do the stats apply to normal, then back transform for meaningful outcomes. Is that they're asking, is that the right interpretation?
Yep, that is what I was getting after. And this is where I think it is really important to remember what it is that we're calculating. Generally, I can say, yes, that's what I meant, and that's what I was saying. But I don't want to say universally that's always going to be true. And that's why the units that we were talking about and actually understanding the formulas, even if you're not going to memorize the formula, to be able to see the formula of a variance or see the formula of standard deviation and follow the units along can give you a lot of information of whether or not that this transformation and then the back transformation or the retransformation is applicable or not. There are going to be situations where that doesn't mean anything anymore because of that, or that the transformation is actually more complex because of the calculation that was. And so in general, yes, it's certainly true. And to mention that, actually understanding the individual formulas and how they're obtained and how they are used will inform that as well.
Okay. And we have another question that just came in about, I'm going to go to this next one, is about how can the data obtained from the square root form of distribution be related back to the original data values?
Yeah, so kind of continuing on what we were just saying. In the brief example that I gave, if we're taking the square root, the opposite of that, the inverse of that function is to square the value. But again, depending on what statistic, what calculation, how you're using these things, for standard deviation, let's say for that example, the standard deviation is in the units of what you're talking about. So taking the square root of that, to reverse it, you just square it. That's very simple. If you're dealing with something that's a bit more complicated, it might be a bit more of a lift to get it there.
Okay, and then the other one is there's variable data on what is acceptable percent RSD or CV values. For example, below 10%, below 20%. Can you comment on that?
Yeah, great question, Ellen, and I've thought this myself. But I'm going to ask a question to your question, which is, you tell me what's acceptable. What are you using the data for? How is it going to be applied? And what are you measuring? What is the CV? I'm thinking you might be thinking along the lines of quality control, which we'll talk about in session 4. But if you're talking about validation or something else, it's really going to depend on, is the tolerance for 10%, 20%, 30%, is it relevant? Depends on the application, it depends on the risk, it depends on how much data you have. You have to ask kind of all these other questions to try to come to that. It is certainly a commonly asked question of like, where does 20% come from? And when I started in toxicology, we talked about quality control acceptance criteria was always plus or minus 20%. Where does that come from? I'm not going to tease you with it, but I am going to ask you, if you're participating today and you have some insight of that, I'd love for you to share it in the chat. I've asked that question many times myself. I've been asked that question many times. I have a couple of theories about it, but I don't have a definitive answer for it. But it is certainly a relevant question. And more so, like, where did it come from? Is it good enough? Is it appropriate? And to that question is my slew of other questions. What is it used for? What happens if it's too wide? What happens if it's too narrow? And can you accept that?
All right. If we don't have anybody else thinking about questions, I think we're going to slide up. Yep. All right. So if we don't have any more questions, we will go ahead and close out today. So thank you everyone for joining us and our guests for providing their expertise in this. And we'll answer any other questions that you come up throughout the weeks at our kind of fireside chat on the 6th session. And also like to mention that the series is meant to provide attendees with some of the relevant data sets to demonstrate principles and teach some of the critical thinking specific to forensic toxicology. But we have said in the beginning of this, it's not in lieu of some of the academic courses that you could take. And so the slide here that we're showing is a list of couple of example resources that provide more in-depth instructions on topics. Some of you may have heard it during Sue's presentation today or some of the ones following. And then we're also compiling a more comprehensive list that can be found on the webinar webpage, or you can scan the Q card there. So I hope everyone enjoyed the presentation today, and we hope to see you on our third session, which is statistical test and hypothesis testing on Thursday, May 30th. Thank you, everyone.
Thanks, Catherine.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.